In this video, we're going to do a rotations FRQ. So the disk shown above spins about the axle at its center. A student's experiment reveals that the disk, while spinning, has friction between the axle and the disk, and it exerts a constant torque on the disk. At time t is equal to 0, the disk has an initial counterclockwise positive angular velocity omega initial. The disk later comes to rest at a time t is equal to t1. On the grid below, sketch a graph that could represent the disk's angular velocity as a function of time t from t is equal to 0 until the disk comes to rest at time t is equal to t1. On the grid on the right, sketch the disk's angular acceleration as a function of time t from t is equal to 0 until the disk comes to rest at time t is equal to t1. So what we have is that the friction is producing a constant torque, and torque is equal to moment of inertia times your angular acceleration. And because our torque is going to be constant, that means that the angular acceleration also has to be constant as well. And we also know that friction here is going to exist, and we know that friction, it opposes motion. That means that the acceleration is going to be negative. So now we can answer this question. For angular velocity versus time, we have initial. On the grid at the left below, sketch a graph that can represent the disk angular velocity as a function of time t from t is equal to 0 until the disk comes to rest at t is t equal to 1. On the graph on the right, sketch the disk angular acceleration as a function of time t from t is equal to 0 until the disk comes to rest at t is equal to t1. So what we have here is, with rotational kinematics, we have that torque is equal to I times alpha, and angular acceleration is going to be constant because torque is constant, and I is also going to be constant. So all three of these are constant. Therefore, we have that angular velocity, which is going to be delta omega is equal to change in angular displacement over time, is going to decrease linearly. And that's because angular acceleration is the change in omega over time. So that means when t is equal to 0, omega is equal to omega initial. And then at t is equal to t1, we have omega is equal to 0. Here omega is equal to 0. At t is equal to t1. So that's just going to be a straight line from omega initial down to 0. So for angular acceleration versus time, we already know that friction torque is going to be constant. And that means that angular acceleration is also going to be constant. And since we know that friction is going to slow down the disk, that means that your angular acceleration has to be less than 0. So that's why we're going to be a horizontal line below 0 for our angular acceleration. For our rotational inertia, we're going to derive this in the second part. So the magnitude of frictional torque exerted on the disk is equal to t initial. Derive an equation for the rotational inertia I of the disk in terms of t initial, omega initial, t1, and physical constants as appropriate. So what we have is that rotational inertia is equal to the torque, which is equal to I times alpha. And because our friction is going to oppose the motion, torque is equal to the negative of torque initial. Angular acceleration is going to come from kinematics, and we have constant acceleration here. So we use the very first kinematics equation, omega f is equal to omega initial plus angular acceleration times time. And we are going to end at rest, so omega f is equal to 0. So now you just subtract both sides. You're going to subtract omega initial, and then you're going to have negative omega initial is equal to angular acceleration times time initial. You divide both sides by time initial, and then you get your angular acceleration. So you're going to take that angular acceleration and you're going to substitute it back into your first equation. After that, you subbed it in. You can divide both sides by that negative since it's on both sides, and then you just divide both sides by I here. You multiply by 1 over t initial, the reciprocal of t initial, to isolate your I. And then after that, you just take the reciprocal, so you get it in terms of I, not over 1 over I. So that is how you get that expression. So now for this part, in another experiment, the disk again has an initial positive angular velocity omega initial at time t is equal to 0. At time t is equal to 1/2 T1, the student starts dripping oil on the contact surface between the axle and the disc to reduce the friction. As time passes, more and more oil reaches that contact surface, reducing the friction even further. On the grid below, sketch a graph that could represent the disk's angular velocity as a function of time from t is equal to 0 to t is equal to t1, which is the time at which the disk comes to rest in part A. On the grid on the right, sketch the disk's angular acceleration as a function of time from t is equal to 0 to t is equal to 1. So the reason why for this graph, when you are at t is equal to 1/2 T1, the oil, that is going to be the point right here where you are going to have the oil start reducing the motion. So as more oil arrives, that friction is going to continue to decrease. So because your torque is going to decrease and we have that torque is equal to I alpha, that means that your angular acceleration magnitude is also going to decrease in that equation because they're directly related. So because the disk is going to slow, we know that it's going to slow less and less strongly. It's going to slow less and less strongly. So that's why we have that curve and not a straight line. So before we have the oil, we have a constant negative acceleration, the exact same as we did above here in this graph. But then, and it's going to be a straight line down. So we're on the way down. But then after the oil, the acceleration is going to become less negative. So it's still negative. It's still a negative slope, but it's going to be not as negative. So instead of it, for example, being like -5, it would be -1. So the slope's magnitude would be less. So the disk is still going to slow down here, but it's slowing less and less strongly. And the slope is going to increase towards 0. So here our slope increases towards 0. We're getting towards 0, but it's getting less negative. And when it's becoming less negative, that means it's also becoming more positive because it's getting closer to 0, and closer to 0 is closer to positive. So that's why your velocity curve is going to start to flatten as you approach 0 and you go to the right into infinity. So you also have to note that the disk has not stopped yet at T1 because the friction has been reduced. Not stopped yet. Only your FF, it's just been reduced. So that's why your velocity, it's gonna stay above 0. It stays above 0 because that is what it's going to serve for the purposes of this question. Now for your angular acceleration, before your oil, your friction torque is going to stay constant and your acceleration constant is still going to be negative. So it's going to be the same acceleration because this is cake. Well, something you should always know for these types of questions in AP Physics 1s is that you always have, most of the time, a constant acceleration. So that means that your acceleration is going to be the same when you graph it. So it's going to be most of the time a horizontal line when you have your acceleration, and if it's constant, that's how you know it's a horizontal line. But here we have that it's going to be after the oil, it's going to have a friction that is going to decrease over time. So here your FF decreases over time. So that means that the magnitude of your angular acceleration is going to decrease. So then your graph is going to be a constant negative and it's going to increase towards 0. But it's still going to remain 0 because the friction is slowing the disk. It's going to remain 0 because it's going to remain negative. It's still going to be underneath 0. So a student is trying to mathematically model the magnitude of tau of the torque exerted by the axle on the disk when the oil is present at times t is greater than 1/2 T1. The student writes down the following two equations, each of which includes a positive constant C1 or C2 with appropriate units. Torque is equal to C1 T minus 1/2 T1 for t is greater than 1/2 T1, and torque is equal to C2 divided by t plus 1/2 T1 for t is greater than 1/2 T1. Which equation better mathematically models this experiment? So in our experiment, we know that oil is going to reduce our friction, so that decreases friction. And we know that that means that the friction is going to continue to decrease over time as more oil is added. Continues to decrease over time. Therefore, torque is going to also decrease with time because torque is going to be caused by the friction. So in equation 1, we see that for t is equal to 1/2 t1, that means that as time increases, that means that torque is going to increase with time, and this is going to contradict the experiment. So this means that this equation is not going to be plausible. Now for equation 2, we see that as your time increases, you see that the denominator increases. So as t increases, your denominator is going to increase. So that means that your torque is going to increase as well. Or sorry, that means that your torque is going to decrease because we see that the time is in the denominator, the torque is in the numerator. So this is going to match with our experiment where our oil is going to reduce friction with time as time goes on. So this means that equation 2 is our better answer. So the reason why is because equation 2 predicts torque decreases over time, which matches the situation where oil progressively reduces friction. So in our equation 1, on the other hand, we saw that it predicts that torque is going to increase with time. And that we saw that it contradicts our experimental description.